A cathode ray tube relies on a vacuum to allow electrons to travel unimpeded from an electron gun to a phosphor-coated screen. Without this sealed environment, air molecules would scatter the beam and prevent image formation. The tension lies in how invisible particles create visible light through controlled collisions within a fragile glass envelope. Now that we understand the basic containment structure, let's examine how electrons are actually generated inside this tube. The process begins at the electron gun assembly, where heat is applied to a cathode material. This thermal energy overcomes the binding forces holding electrons in place, allowing them to escape into the vacuum space. We will trace their path from emission through acceleration and toward the screen surface. To understand how old televisions created images, we must first examine the physical container known as a vacuum tube. This device requires an internal environment devoid of air molecules to allow electrons to travel unimpeded from the rear gun to the front screen. Without this vacuum state, fast-moving particles would collide with gas atoms and scatter before reaching their target destination. The glass envelope is engineered with varying thicknesses, where the funnel shape at the back reduces surface area stress, while maintaining structural integrity under atmospheric pressure. Inside this sealed chamber, the inner face of the screen is coated with a thin layer of phosphor compounds that emit light when struck by high-energy electrons. For instance, different chemical formulations within this coating produce specific colors like red or blue depending on the excitation energy level applied. This precise arrangement ensures that only the intended areas glow while maintaining the necessary conditions for particle acceleration and control. Once we understand how the screen is prepared to receive these particles, we can explore exactly where they originate within the system. Pause 0.8 to create an image on a cathode ray tube display. We must first generate a controlled stream of freed electrons. This process begins at the electron gun assembly through thermionic emission, where heat liberates charge carriers from a solid surface. The cathode is constructed from materials with low work functions, such as barium oxide coated on a nickel sleeve, which allows electrons to escape when heated. A filament within this structure raises the temperature of the cathode to approximately 800 degrees Celsius. At this thermal energy level, electrons gain sufficient kinetic energy to overcome the binding forces holding them within the metal lattice. For example, as the heating element activates, you will observe a visible glow indicating the onset of electron release into the vacuum path. Without this precise temperature control and material selection, the necessary density of free electrons would not be available for image formation. Pause 0.8. Once we have a stream of free electrons from the heated cathode, we must control their energy and direction to form an image. The first step involves applying a high voltage potential difference between the cathode and the anode structure inside the tube. This electric field exerts a force on each electron, causing them to accelerate rapidly toward the front of the screen. Think of this like gravity pulling a falling object faster as it descends, but here the electrons reach speeds approaching 1/3 the speed of light. However, a fast beam is useless if it spreads out and hits the glass randomly rather than forming a sharp spot. To solve this, we use electrostatic lenses formed by grids held at specific voltages relative to the main anode. These grids create curved electric field lines that act like optical lenses for light, bending the electron paths inward toward a central axis. As the electrons pass through these focusing fields, their trajectories converge until they meet at a single precise point on the phosphor coating. Without this convergence, the image would appear as a blurry wash of color instead of distinct pixels or lines. Now that we have a fast, focused beam ready to strike the screen, we need a way to move it systematically across the surface. This brings us to the mechanism responsible for scanning the beam in precise horizontal and vertical patterns. Pause 0.8 to understand how old televisions formed images. We must examine the magnetic deflection system that steers the electron beam across the screen. The core mechanism relies on the Lorentz force, which acts upon moving electric charges when they pass through a magnetic field. External coils wrapped around the neck of the cathode ray tube generate these controlled magnetic fields to deflect the electrons horizontally and vertically. When current flows through the horizontal deflection yoke, it creates a magnetic field that pushes the beam from left to right in a rapid scanning motion. Simultaneously, vertical coils modulate this flow to move the beam downward line by line until the entire phosphor screen is illuminated. Consider the contrast with electrostatic steering used in oscilloscopes. Television tubes required magnetic fields because the high-velocity electrons needed stronger deflection forces for larger screens. The precise timing of these currents ensures that each electron strikes its designated location to build up the complete picture frame by frame. Pause 0.8. While monochrome tubes relied on a single uniform phosphor layer to produce grayscale images, color displays require a fundamentally different approach to generate the full spectrum of visible light. The interior surface of a color screen is coated with microscopic clusters of red, green, and blue phosphors arranged in precise geometric patterns known as triads or stripes. To ensure each electron beam strikes only its designated color, a perforated metal shadow mask sits just behind the glass faceplate, acting as a physical alignment guide for 3 separate electron streams. As the beams pass through specific holes in this mask, they converge at exact points on the phosphor layer so that red electrons excite only red dots, while green and blue remain isolated from their counterparts. This mechanical precision means even minor misalignment can cause color fringing or washed-out images, because the electron streams must maintain strict spatial correspondence with the underlying phosphor clusters. Understanding this physical separation mechanism sets the stage for examining how electronic signals synchronize these beams to paint coherent pictures across the screen. Pause 0.8 to reconstruct a coherent image on an old television screen. The broadcast signal must precisely coordinate the movement of the electron beam across the phosphor-coated display. This coordination relies on synchronization pulses embedded within the video signal that dictate exactly when the beam should begin its horizontal scan line or vertical frame reset. For instance, a sharp horizontal sync pulse triggers the rapid return sweep of the beam from the right edge back to the left side at the start of each new row. Without these timing signals, the electron stream would drift out of alignment, causing the image to tear horizontally or roll vertically as the scanning process loses its reference points. The vertical sync pulses operate on a slower timescale, ensuring that after completing all horizontal lines, the beam resets to the top of the screen for the next full frame. Understanding this temporal framework is essential before we examine how the beam actually excites the phosphor materials to generate visible light. Pause 0.8. The core mechanism relies on a specialized material called phosphor coating applied to the inside of the screen. When high-speed electrons strike these microscopic grains, their kinetic energy transfers directly into the atomic structure. This impact excites electrons within the phosphor atoms, pushing them from a stable ground state into a higher energy orbital level. Because this excited state is unstable, the internal electrons immediately return to their original configuration. During this relaxation process, the excess energy is released as discrete packets of light known as photons. For instance, a copper-doped zinc sulfide grain will emit green light when struck by an electron beam at specific voltages. This precise conversion of kinetic motion into visible radiation creates the bright pixels we perceive on the display. Understanding this atomic interaction sets the stage for analyzing how our eyes integrate these rapid flashes into a continuous image. Pause 0.8. The image on an old television screen is not actually continuous, but constructed from discrete flashes of light. When the electron beam scans across the phosphor coating, each point glows briefly before fading as the beam moves to the next location. This rapid scanning cycle relies on a biological property called persistence of vision, where the human retina retains an image for approximately 100 milliseconds after stimulation ceases. Because the screen refreshes at rates exceeding 50 times per second, individual flashes merge into a stable perception through a process known as flicker fusion. For example, if you observe a spinning fan blade under fluorescent lighting, It may appear to stop or move slowly due to similar temporal integration effects in your visual system. The television exploits this neural delay by ensuring that the next frame arrives before the previous one fully dissipates from conscious awareness. Pause 0.8. The CRT operates by generating, accelerating, and deflecting an electron beam within a vacuum to strike phosphors that emit light upon impact. This process requires precise synchronization between signal timing and mechanical components to reconstruct images frame by frame.